excited about talking about three-phase circuits. If you're even thinking about being a lineman, you really need to understand these ideas and be familiar with them, be able to work on them. And so it's interesting stuff. I think you're going to enjoy this. Okay, we're going to discuss difference between three-phase and single-phase voltages. We're going to talk about delta and Y connections. We're going to compute voltage and current values for delta and Y connections. And we're going to compute the amount of capacitance needed to correct the power factor of a three-phase motor, although we've already done that before, right? Okay, the advantages of three-phase horsepower. Three-phase motor will develop a lot more power than the same size single-phase motor. Okay. Power delivered by single-phase systems falls to zero constantly, right? Every 240th of a second, it falls to zero or thereabouts. That's probably an incorrect estimate of the time, but a very small amount of time, but it happens, what, 60 times a second? It falls to zero. Okay, three-phase systems don't do that. Okay, so the power is always happening. And there's a picture of the power happening in three different phases, and you know the red, notice the red lumps on top and the red lumps on bottom is indicating that the power is always being generated. Okay, three-phase circuits, each phase is 120 degrees apart. They happen 120 degrees of phase angle later than the one before it. Okay. Three-phase systems have 3 or 4 conductors. We always call them A, B, and C. Phase A, phase B, phase C. The fourth conductor, if you have one, is a neutral, and that'll generally be in a Y system. The Y, or star as it's called, is made by connecting one end of each phase winding together in a common node, a common point, a common place to tie them together. And then that is taken to ground. Okay, each phase winding has a voltage drop known as the phase voltage. The line voltage is measured from the phase conductor to the different phase conductors. Okay, so phase voltage is from a single phase to ground, and line voltage is phase to phase. It's a very important idea that you understand. Okay? In a Y system, the line voltage is higher than the phase voltage. That should be the other way around. That should be stated the other way around, in my opinion. The phase voltage times the square root of 3 is the line voltage. Let me say that again. The phase voltage times the square root of 3 is the line voltage. And that's our formula here. Phase voltage times square root of 3 is the line voltage. And a Y connection, the line current is equal to the phase current. So it's like when we were talking about series circuits and parallel circuits. So here we have a place where the current is constant, sort of like a series circuit, right? And here we see a picture of a three-phase circuit. And if we have, let's say, 277 volts across a phase, multiply that times square root of 3, and we'll have approximately 480. Okay, and then our currents would be the same, whether it's across a phase or across the line. I want to point out why this is. I said that this is similar to a series circuit, right? And I want you to take a note of, look at this point right here, and look at this point over here, and you'll notice that the current is going through that point in a series method, right? So the current has to be constant in both these places, right? Whether you're measuring from here to here, or from here to here, it's got to be the same, right? Okay. Alrighty then. Now I can't get it to move the slide. Alrighty. There we go. Vector sum of typical Y system voltages. I think this is not a very good picture. It's not making it terribly clear what everything is going on here. But we're going to do a lot of examples with this, so don't worry about that. Okay, now we're going to talk about delta connections. Completely different. Okay, a delta system, the line current is higher than the phase current by a factor of the square root of 3. In other words, it's the same rule. The phase times square root of 3 is the line, except now we're talking about the current. Okay? Now, because that's reversed from the other type, we're going to have a reversal on the voltage because the voltage is going to be constant, like a parallel circuit, because it is a parallel circuit. Here we have a picture of a three-phase delta setup. And you'll notice that if you look again at phase to phase or phase to phase, they're parallel circuits, right? And then if we look at this one, that one's in parallel with the other one. So this is like a parallel circuit. And in parallel circuits, voltage is constant, right? So it's easy to remember now, right? So voltage is constant, and the phase current times square root of 3 is the line current. So now we have the 4 rules you need to know about in delta and Y three-phase circuits. Okay, and you can see that the current going in on one phase can be measured. How could we measure this with a meter? We can measure the phase current, and we can measure the line current, maybe. If it's a parallel circuit, how can we read the current for the phase or the current for the line? Okay. Three-phase power. Three-phase power can be computed in 2 ways, using line values or phase values. Now, I suggest you don't try to remember both of these formulas. I suggest that you remember one and the other one will come to you because that you remembered one. Now, in phase voltages, I want you to take a look at this. It's nice and simple. Phase voltage times phase current times 3. So one transformer's power, one winding's power, times 3 is the total power, assuming they're all equal, right? Okay. But if we use the line voltage, we have to multiply the square root of 3 times the phase voltage and the phase current. So the oddball is when you're using line values, you have to multiply times the square root of 3 instead of 3. So the easy one to remember, in my opinion, is phase values. And besides, one of the rules we're going to start using is when we're doing three-phase circuits, stay in phase whenever possible. Look at phase, because we'll do a drawing later and we'll look at what you're looking at is what's happening from one winding to the next winding. And that's a relationship you need to look at. Line values don't always reflect that information properly or easily understood. Okay, so three-phase power, you can figure out the power or the true power, right? The apparent power and the true power. What's the difference between power and true power anytime? You take the apparent power and multiply it times the power factor, and you get your true power, right? Same thing with three-phase power. So we can take the formula for power for phases, and we multiply that times power factor, and we get the true power. And this should not say just P over here. This should say true power. Okay, up here, true power, square root of 3 times the line voltage times the line current times the power factor. Just like any other time we're calculating true power and apparent power, which we've done a lot of times in the past. Okay. Three-phase circuits. Notice that we have a Y alternator. And what does that mean if it's an alternator? It's making AC. because generators make DC, even though we call most alternators that have a portable little alternators are usually called generators, but that's a whole different Oprah. And notice that we have a delta load connected to a Y supply. Now, you can only see what's being transferred from one to the other on the line voltages, right? But still you want to look at what is happening from phase to phase whenever possible. Okay? And in this one, we're going to say that this is simple resistance so that we don't have to compute the phase angle, but usually we do with a motor, right? And now we have two different loads where we're going to have an alternator producing three-phase power, a Y load, and a delta load. And then we can add a capacitor. How are these capacitors wired to the other two loads? In a Y. Okay, they're in a Y, but they're kind of parallel to everything else, right? Okay. The voltage of three-phase systems are 120. We've said that about 10 times. Oh, this is a review of everything we just gone over. Good deal. Let's stop this now, and we're going to make this a separate one at a mere 12 minutes for one.